Hi, we are from Group 15 and we are going to talk about biosynthesis and metabolism of purine and pyrimidines. My name is Tong Lap Cha and first of all, let me show you about the structures. As you can see here from pyrene and pyrimidine, purine consists of 6-membered and 5-membered nitrogen-containing ring that is fused together, while the pyrimidines only have 6-membered nitrogen-containing ring, making it bigger than purine. And then we continue to the family member that is usually can found in pyrene and pyrimidines. Those are the family members. And then finally, we are going to talk about the function. There are major energy carriers and subunit of nucleic acid. There are also precursors of synthesis nucleotide cofactors. Usually they are found in amino acids and they are very important specialized pathways of amino acids. Those are the things I'm going to talk about in introduction. Continue on with my friends.
De novo synthesis of purine and pyrimidine. In de novo synthesis of purine, inosine monophosphate (IMP) is the first nucleotide formed. It is then converted to either AMP or GMP, adenine and guanosine monophosphate, ribose triphosphate, from glucose, and a great deal of energy in the form of ATP is important in this synthesis. In the first step, purine synthesis, ribose phosphate pyrophosphokinases activates the ribose 5-phosphate R5P by reacting it with ATP to form 5-phosphoribosyl alpha pyrophosphate PRPP. Next, PRPP is replaced the amide group of glutamine by amidophosphoribosyl transferase to form 5-phosphoribosylamine PRA. By following the remaining 9 steps, the first purine derivative that is synthesized is inosine monophosphate IMP. IMP is the precursor for the purine nucleotide adenosine and guanosine monophosphate AMP and GMP. Each are synthesized in two reaction pathways with bifurcates at the level of IMP. GMP formation requires the IMP to be first oxidized to xanthosine monophosphate using NAD. Similarly, GTP provides the energy to convert IMP to AMP. In this reaction, the monophosphates are readily converted to di- and triphosphate. De novo biosynthesis of pyrimidine. Unlike the synthesis of purine nucleotide in pyrimidine synthesis, 6-membered pyrimidine ring is made first and then attached to ribose phosphate, which denoted by PRPP. Amide provide nitrogen in atom 3. Dioxide provide carbon in atom 2. Aspartic acid furnish carbon in atom 4, 5, and 6, and nitrogen in atom 1. The first step is synthesis of carbonyl phosphate from carbon dioxide derived from bicarbonate and ammonia derived from glutamate by carbonyl phosphate synthesis 2 (sp2). Second step is carbonyl phosphate combined with aspartate in the presence of aspartate transcarbamylase to synthesize carbonyl aspartate. This particular step is committed step of pyrimidine synthesis. Next, ring closure of pyrimidine occurs by dehydroorotase to synthesis dehydroorotate. Catalyzed by dehydroorotate dehydrogenase, which remove hydrogen atom from dehydroorotate to synthesis orotate. Next, donation of PRPP for ribose phosphate by orotate phosphoribosyl transferase to synthesis orotidine monophosphate OMP. Carboxyl group remove carbon dioxide by OMP decarboxylase need to synthesis uridine monophosphate UMP. Uridine monophosphate phosphorylated with kinase enzyme to synthesis of uridine diphosphate UDP. Uridine diphosphate then synthesis other pyrimidine nucleotide like uridine triphosphate, cytidine triphosphate, thymidine monophosphate, and deoxyridine diphosphate.
The end product of purine catabolism in man is uric acid. Other mammals have enzyme urate oxidase and excrete the more soluble allantoin as the end product. Man does not have this enzyme, so urate is the end product for us. Uric acid is formed primarily in the liver and excreted by kidney into the urine. Guanine nucleotides are hydrolyzed to the nucleoside guanosine, which undergoes phospholysis to guanine and ribose 1P. AMP is deaminated by enzyme AMP, deaminase to IMP. IMP is further degraded by hydrolysis with nucleotidase to inosine, then phospholysis to hypoxanthine. Both adenine and guanine nucleotides converge at the common intermediate xanthine. Hyperxanthine, representing the original adenine, is oxidized to xanthine by the enzyme xanthine oxidase. Guanine is deaminated, with the amino group released as ammonia to xanthine. Xanthine, like hypoxanthine, is oxidized by oxygen and xanthine oxidase, with the production of hydrogen peroxide. In human, the urate is excreted and the hydrogen peroxide is degraded by catalase. Xanthine oxidase is present in significant concentration only in liver and intestine. In a situation of high concentration of urate in the blood, we cause a common disease known as gout, in which a deposition of sodium urate crystal in joints and tissue that causes extreme pain. The repeated attacks will lead to destruction of tissue and severe arthritic-like malformation. Pyrimidines undergo ring cleavage and the end product are beta amino acid plus ammonia and carbon dioxide. Pyrimidines from nucleic acid are acted upon nucleotidase and pyrimidine nucleoside phosphorylase to yield the free bases. The fourth amino group of both cytosine and 5-methyl cytosine is released as ammonia. In order for the rings to be cleaved, they must first be reduced by NADPH. Atoms 2 and 3 of both rings are released as ammonia and carbon dioxide. The rest of the ring is left as also known as beta amino acid.
Salvage of base is pathway in which a biological product is produced from intermediates in the degradative pathway of its own or a similar substance. It used to recover bases and nucleosides that are formed during degradation of RNA and DNA. It's important in some organs because some tissues cannot undergo de novo synthesis. Salvage pathway for purine nucleotides. Location. Purine synthesis via the salvage pathway occurs in all tissues. It is especially important in the brain and the bone marrow. Phosphoribosyl transferase at activated ribose 5-phosphate PRPP to bases, creating nucleoside monophosphate. There are two types of phosphoribosyl transferase. The first one is adenine phosphoribosyl transferase APRT and hypoxanthine guanine phosphoribosyl transferase HGPRT. HGPRT is an important enzyme in purine pathway metabolism and its deficiency is implicated in Leigh-Nahan syndrome. The parasite Plasmodium falciparum relies exclusive on the purine salvage pathway for its purine nucleotides requirements. Nucleotides catalyze the hydrolysis of purine mononucleotides to their respective nucleosides and phosphate. The nucleosides are taken up in the cell by transporters and are funneled through the salvage pathway. If the nucleoside is adenosine, it is acted upon by the adenosine deaminase to convert it into adenosine. It is acted upon by purine nucleoside phosphorylase and is converted to hypoxanthine. Hypoxanthine is acted upon by HGXPRT in the parasite to convert the respective nucleobase to its nucleotide monophosphate respectively. Salvage pathway for pyrimidine nucleotides. Salvage of pyrimidines is not as significant as it is for purines. Only 30% of pyrimidine nucleotides are provided by the salvage pathway. Pyrimidine nucleosides travel in the blood and are taken up by the tissues. Uridine phosphorylase adds ribose 1-phosphate to the free base uracil, forming uridine. Uridine cytidine kinase can then phosphorylate these nucleosides into uridine monophosphate UMP. UMP or CMP kinase can phosphorylate UMP into uridine diphosphate, which nucleoside diphosphate kinase can phosphorylate into uridine triphosphate. Thymidine phosphorylase adds 2-deoxy-alpha-D-ribose 1-phosphate to thymine, forming thymidines. Thymidine kinase can then phosphorylate this compound into thymidine monophosphate TMP. Alternatively, uridine cytidine kinase can phosphorylate them into cytidine monophosphate CMP or deoxycytidine monophosphate DCMP. The nucleosides cytidine and deoxycytidine can be salvaged along the uracil pathway by cytidine deaminase, which converts them to uridine and deoxyuridine, respectively.